So if I can get your attention. So last time we covered probably the most important part of this chapter, lumped capacitance. Why is it so important? Well, because you can readily make some good predictions of temperature as a function of time for some simple systems. Now we're finally going to get to calculating the temperature, not just as a function of time, but also of space. Is there anything meaningful or significant about which variable comes where? Not really. I could put t of x comma time or x, time space x. So anyway, now we're going to consider spatial effects. Well, remember this? This was helping us motivate our study of lumped capacitance method. Some example, here's a large sheet of some material. Think about it being very large, but very thin, and the thickness is 2L. So the half thickness is L. It comes out of a furnace. It's hot. It's going to be convectively cooled when it's subjected to fluid, both on this side and that side. The temperature profile inside the object could look like case A, where you have it relatively flat within the system, within the object, and then the majority of the temperature difference between the object and the fluid is concentrated in the fluid layer, the boundary layer, the convection. Okay? Or it could have some significant temperature variation within the object, like case C, and very small temperature difference between the surface of the object and the fluid, hence in the boundary layer and convection. So that then that leads us to a good clicker question, or a few of them. So let's go ahead and ask this question here. Get rid of this one. Get it out of the way. Which case is the lumped capacitance model justified? Case A, B, C, or none, or it can't be determined? Which case, A, B, C, or can't be determined, is the lumped capacitance model justified? All right, so everybody's in. Let's stop. And we stop and we show the results. Well, it's justified for case A, isn't it? Case A? So that's the case visually. Don't lose sight. I know we can get bogged down on the math. Oh, let's check this number. Is it big? Is it small? I don't know what the number means, but I know what to do. All right, now let's try this next clicker question. So, which case has the greatest BO number? The largest BO number. All right, so everybody's in. So what do we recall? We recall that we had a test for the justification of lumped capacitance. We said we're going to calculate this BO number. It's H L sub C divided by K. If the BO number is much, much less than 1, if it's small, we will use lumped capacitance. It could be the BO number is around 1. Don't use it. It could be the BO number is even greater than 1. Definitely don't use it. So which case would this be? The greatest BO number is the one that's farthest away from justifying lumped capacitance. Which case is farthest away? C. C is farthest away. It has the greatest BO number, doesn't it? All right. So now we'll ask this question. Which case, A, B, or C, has the greatest Fourier number? The Fourier number. A, B, C, or none that can't be determined. Which one has the greatest Fourier number? Professor, can you remind me what the Fourier number definition is? Okay. The Fourier number is alpha t divided by L squared. That's the Fourier number. Is everybody in? All right, we'll go ahead and stop and we'll talk about it for a minute. Well, I forgot, Professor. What is alpha? Thermal diffusivity, K divided by rho C. It's just a property like K, just like rho, just like C. I can get the thermal diffusivity of the material of interest. What is L? Some length, right? So what is t in this equation? Time. So what's our interpretation of the Fourier number? Dimensionless time? Some thermal dimensionless time? Because isn't this dimensionless? It's dimensionless, not dimensional, dimensionless. So you say, it looks like it's just a scaled time. That's exactly it. What is the difference between this curve, this curve, this curve, that curve? What do they have different between those four curves? Increasing time. Increasing time. That's what they're showing you. They're showing you the transient part of the response. True? So what does it start when they have t at any x 0? What's the 0 standing for? Time equal to 0. Initial temperature profile is uniform in each of these three cases, A, B, C. But then the profile changes shape as I march forward in time. For the first case, it's still pretty flat all the way across, but it's dropping with time. The second case, I have a little steeper, and then I have some significant steepness or distribution, variation of temperature within the solid. So that's what the Fourier number is showing you, dimensionless time. So when I say case A, B, or C, you're showing multiple Fourier numbers or multiple times at which the temperature profile is plotted. Which answer then makes the best sense? How about this? I'll give only 20 seconds to answer a new question, which is the same question. You only have 20 seconds. I just spent a lot of time talking about it. All right, we stop. Sometimes I wonder why I'm doing this, right? I'm doing it for the paycheck. But if nobody learns, maybe I should give the paycheck back, right? You ever thought about that? I used to think about that when I was a student. This turkey's getting a paycheck. For what? I have no idea, but I am sure not learning. Okay, the best answer is it can't be determined. It can't be determined. There's a bunch of different cases of time shown in each of these cases, A, B, and C. It's like the Fourier number for this first curve, that may be, that definitely is 0. And then maybe the Fourier number on the second curve was, 0.1. Then the Fourier number is 2, and the Fourier number is 10. I don't know. I'm just making some numbers up for the Fourier number. I think those are too high. All right. So D is the best answer. So let's go back and see 29% after discussion. Oh, come on. You guys were... I made you dumber. What happened? That hurts. That hurts. Now let's think about it. We're going to pose, this whole section is very mathematical. It's very mathematical. Okay, what we're going to do is we're going to solve for the temperature profile as function of time and space in this domain and be able to plot it and get curves like that. True? So what we're going to have to do is get a differential equation for the heat transfer, something like second derivative of temperature with respect to space equal to 1 over the thermal diffusivity, first derivative of temperature with respect to time. I'm going to solve that equation. Let me ask this. Is it an ODE or a PDE? It's a partial differential equation, and I tried to be careful to put partial derivatives because this temperature is a function not just of x or not just of t, but of both of them. So I have two independent variables. It's a partial differential equation. Okay, it's second order in space. How many boundary conditions do I need? 2. It's first order in time. How many initial conditions do I need? It's first order in time. I need 1 initial condition. When you were over in dynamics, you had to not only know the initial position of the object when you let it go and it started to oscillate and vary back and forth, but you had to also specify the initial velocity because it was second order in time. You had two initial conditions. But anyway, so we need boundary conditions, two of them. So let's talk about this boundary condition right here. What is the correct mathematical statement of the boundary condition at the location x equal to 0 for this problem? A, B, C, D, or E? Professor, where's x equal to 0? Where is x equal to 0? Center line. The center line. Exactly. Everybody in? Let's close it down. Everybody in? And we stop. So, okay. In words, what is the appropriate boundary condition at the center line? In words, without putting it into equation first. Say it in words. It's symmetrical about that center line. I can cut it in half and flip the right over to the left and it'll lay exactly on it. Or I could flip the left over onto the right. It's symmetrical. Isn't the temperature distribution symmetrical at all times about the center line? So then we think, what was our favorite boundary condition for symmetry? Wasn't it? We covered that before in other section, other lecture. So let's go ahead and see how we did. Oh, we did pretty good. Did pretty good. What is the appropriate boundary condition at x equal to L? I need two boundary conditions. What is the appropriate mathematical statement of the boundary condition at x equal to L? Everybody in? All right, let's go ahead and stop. Let me add to the discussion a little bit here. How does the heat get transferred out of the object and into the fluid? C-O-N-V, convection. Convection. It happens right here at this edge. So we write a little control volume around that edge. Right? At the edge. Just a very thin control volume. On the right side, it's a little bit into the fluid. On the left side, it's a little bit in the solid. So how does it get out by convection? How does it get in by conduction? So at that boundary at x equal to L, we write that Q double prime conduction moving in the positive x direction is equal to Q double prime convection in the positive x direction, getting off of the surface into the fluid, right? This is the positive x direction. We use minus k dt, or put a partial derivative, partial t with respect to space at x equal to L. And then for our convection, we have h times the temperature of the surface at x equal to L, which is L comma any time t, minus t infinity. Why is this a temptingly wrong answer? Because sometimes people look at it and say, the surface temperature immediately goes to the fluid temperature. But it's not. It's still a little above until all the heat's out, and eventually then the surface temperature is the fluid temperature, the center line temperature is the fluid temperature. But this is temptingly, it looks like the right answer, but it's not the right answer. Good, right? All right. Well, I thought about not having those questions, not talking conceptually about it, but just going and slugging through the math. I've done it before. I had put a lot of people to sleep. But what I thought I would do is just say, look, this is the math. You have a whole class in ODEs and linear algebra, EA1. You have a whole class in differential equations, vector differential calculus, and all that, EA2. Whole class in PDEs, that's EA2. So it's all within your skill set. You say, it's been a semester. Well, that's just review. So let's do this. We start with this differential equation. True? What is this? Initial condition, boundary condition. I have to have one initial, two boundary conditions. I then introduce theta to help tidy up the math, to make the equations a little more compactly written. I then theta hat. The book likes theta star, but theta has units of degree C. Theta hat is truly dimensionless. So we like to move into this generalized representation of the equation. We get x hat, dimensionless space. We get t hat, dimensionless time. And then we just transform our physical differential equation into a dimensionless representation. It's still a second order in space and first order in time, but it's been cleaned up and packaged nicely. We transform our initial condition, our boundary conditions, and they look a lot more compact. Then you say, I'm going to solve it. Between here and here, there's a few steps. That's your EA2. You get a series solution, something like eigenfunctions, and then the coefficients in front, the C's, and you have what they call a transcendental function to get the eigenvalues, the zetas, in this case, the way they wrote it in this textbook. There's multiple zetas. That's why they put n 1, 2, 3, 4, 5, 6, 7, 8. They can go up to infinity. That's why you have a sum. So we see that this solution has exponential in time. It'll decay in time. And it has some space, which is a sum of cosines, and those coefficients. There it is. There's the analytic solution. When you do it for the radial systems, you get Bessel functions. And it's in the book, but I don't have time, okay? You know what I mean? But what we do is, if you wanted the first four roots or the first four terms of this infinite summation, they've computed them for you as a function of the BO number. Everything depends on that BO number, because right here it is. And they put it into an appendix. And so you can look at the appendix and find what those first four roots are depending on your coordinate system. This is Cartesian. They also do cylindrical and spherical for a range of BO numbers. All right. If you then only really want to have use this equation for large Fourier numbers, and that's not really that large. It's just the Fourier numbers greater than 0.2. What they find is these terms, second, third, fourth, fifth, decay much more rapidly, and they go out of the equation. You only have one term that dominates the whole solution, and so it just goes to one term approximation when the Fourier numbers are just greater than 0.2. Now, it's even simpler if you say, I'm just interested in the centerline temperature for a Fourier number greater than 0.2. Boom. You just get rid of the spatial component right there. It's just a constant, e to the minus zeta 1 squared times Fourier number. How do you like that? Table 5.1 gives you that one-term approximation, the information needed for the one-term approximation of the series. As a function of the BO number for the plane wall, you can get zeta 1 as well as that constant. Now, I cut this table right here, okay? There's a bunch of lines skipped. So we have the top of the table, the bottom of the table. Same thing for the infinite cylinder and for the sphere, zeta and C. All right. Whenever you see a table and you have a little like footnote right here, or a little that's BO number with a little A, what should you do? Well, it's just like a traffic sign on a highway. You ignore it. You go as fast as you want. You know, if it says a curve up ahead, danger, bah, pff, no, read that. So you come down here to the bottom and you try and say, what are they telling me? The BO number is HL over K for a plane wall. That looks familiar. Oops, right here, careful. It's also equal to HR naught over K. The BO number is h r naught over k for the infinite cylinder and the sphere. Go see this figure. You can make an easy mistake here. First thing you do when you're having these problems of cooling a sphere, cylinder, or a plate like this is you check to see if lumped capacitance is justified. True? And you calculate the BO number. Which way? The BO number is equal to H L sub C divided by K, where L sub C for the plane wall is the half thickness L. L sub C for the cylinder is R over 2. L sub C for the sphere is R over 3. Right? You then check, it's not justified. But you already calculated your BO number. But it was based on a characteristic length. You then go and you say, I need the one-term approximation. Same symbol, BI, for BO number. Different length scale. This little lowercase r naught is defined in figure 5.6. Here is the figure 5.6. And you can see what r naught is. It's the radius. So when you're using these one-term solutions or the infinite summation of terms, which the first four are given to you in the appendix, don't get confused. Do not use r over 2 for the cylinder. Use r. Don't use r over 3 for the sphere. Use r. Somebody asked in the earlier class, why didn't they just make these things consistent? And a lot of it's the inertia with the textbooks, and everybody's done it this way. And so, sorry, it's like the English language. If somebody sat down and designed a language for communication, it would not be close to English. It would not be close to Russian or Mandarin or anything else. Does anybody know what the name of the truly scientifically designed language is? There is one out there. What is it? I had a friend years ago, 30 years ago, he would go to conferences where they just get together and they just only speak this language. It is not a dialect that was developed in some region of the country or the world or anything like that. It was designed by those that study languages. Oh yeah. I used to know the name of it, but I can't remember it. It would be so clean in engineering and science if we just sort of erased all of the stuff and said, let's just have a nice purist, just define things perfectly. But that doesn't happen. So you have to be careful. The BO number means different things. Turn the page a few pages in your textbook. The BO number has a different definition. Frustrating to students. That's why they say, why don't they just fix it? Why don't we just fix the English language? Actually, the English language, it would be like trying to lasso something. You can't do it. People invent words and then they just run with it, right? The new word now is huge, right? Thanks to our Trump and Sanders, they both use it. Huge, huge, huge. So I'm starting it too. I'm gonna. In my vocabulary comes huge. Esperanto is it. That's it. That's the language. If you're interested, it's a lot. Did you know it? Yeah. Okay. Do you ever speak it? No. Well, you can speak it. You can write it. You can go to conferences. And my friend told me one time he slipped and went back into English. Ooh, we come all this way to go to Esperanto conference. We only speak Esperanto, period. So anyway, yeah, I forgot the name of that. All right, so be careful there. Let's solve a problem. We have a solid. It's 3 centimeter diameter sphere of glass, which is lime soda. You know what? We solved this problem last time, but last time it was copper. We switched from copper now to lime glass. The temperature, when it comes out of the furnace, 80 degrees C, the same number. It's abruptly removed into 20 degrees C air, same number for the air, same convection coefficient. Only thing is, the diameter's the same. It's just glass and not copper. Well, how does copper compare to glass? Look at the thermal conductivity of copper. Look at the thermal conductivity of glass. What do you think? Big difference. Huge difference. We could take a look at the density and specific heat as well, but the key parameter is the thermal conductivity. It's not going to easily move heat within the object to the boundary so it can be convected away. So the question is, how long will it take for the center of the sphere to be cooled to 50 degrees C? Now this term center really has more meaning, doesn't it? Because we're going to flame off and we're going to say, let's calculate the BO number using the characteristic length, which is R over 3 for a sphere, and we calculate that BO number to be 0.268. Should we use lumped capacitance? Nope. And why is it so high? Well, remember the definition of the BO number? Small k makes for a large BO number. Okay, so there you go. Now let's continue on. Once we just said we cannot use lumped capacitance, we then say, do you think that the time it's going to take will give us a Fourier number greater than 0.2? Otherwise, I've got to go to an infinite series solution, and all I got is 4 terms, or I'm going to hopefully just be down to 1 term. The time, how much cooling? It went from 80 to 50. It's going to go 80 all the way to, 20. So yes, it's most probably going to have a Fourier number greater than 0.2. It's going to take a while for it to cool, to get the center line down to 50. So what do? We say that the theta hat at the center line, which was that? That was the temperature at the center line minus the T infinity divided by the initial temperature minus T infinity. We're interested when that center line temperature is now 50 minus the T infinity 20 divided by 80 minus 20, which is 30 divided by 60, which is 0.5. So theta hat, that dimensionless ratio of temperature differences of interest at the center line, needs to be a half. Okay, we say that this theta hat naught is equal to a constant C1. Forget the cosine of that term because we're doing it at the center line. It's going to be the exponential of what? Negative the zeta 1 squared Fourier number. I know it's a little abstract, but there we go. So to use this, I need to get the C and the zeta. I need to evaluate it as a function of the BO number in the table I just showed. So we recalculate the BO number. This time the BO number is not based on L sub C, it's based on R. So sometimes I add something to try and say, this BO number is based on this BO number is based on that. What's the difference? Only a factor of 3, right? It's only a factor of 3. So the BO number comes in, when you base it on R, of 0.8036. Does this one look like it's 3 times larger? Yeah, pretty close. So that helps me. I didn't make an error there, I hope. Then we jump into the table, and maybe I'll scoot back. Is it right here? Where is it at? Right here. What we do is we'd come down, marching down here, and we would say, okay, 0.8, somewhere is 0.8. Well, I deleted it, okay? But then I would come over, and maybe I have to interpolate to get the zeta 1 and C1 for the sphere. See what we just did? So you get the zeta 1 for the sphere. It's in units of radian. That zeta 1 is 1.435 rad. What, again, is a radian? It's how we measure angles. But how we measure angles is arc length divided by a radius length, so it's really dimensionless. But you can talk about angles in degrees, you could talk about angles in radians, and what's the student going to, when I teach statics, first thing I do, okay, when we start doing angles, get your calculator out. You on your calculator, this is high school stuff, give me the cosine of 30 degrees. And somebody will be invariably, my calculator's broke. It won't give it to. What do you think? They're in radian mode. Yoo-hoo! Right? So anyway, it is a zeta 1 like that. Hopefully you're well beyond that. All right, so C1. So what is C1? We find C1 to be 1.225. So what you do is you say the Fourier number is equal to this theta hat at the center line divided by C1. Take the natural log of that and multiply by 1 over zeta 1 squared. So we calculate the Fourier number. It comes in at 0.4352. Well, you know what? That's better. It's greater than 0.2, so I'm glad we confirmed that that's good to use one term. If you assumed it, but then you got a Fourier number of 0.01, then you would know I have to go back and include more terms. I recall the definition of the Fourier number, which is alpha t divided by L, but in this case it's r squared. Professor, are we sure we want to use r? Yeah, we want to use r. So the time is going to be the Fourier number times r squared divided by alpha. Professor, where is the property alpha given for the glass? You got the 3 components, you have to do the k over rho c. Got it. Thank you. But somebody asked me that earlier. They're like, hey, you didn't give us alpha. I know, but you got to be able to calculate it. And then we calculate the time. Here is 131 seconds. Professor, what happens if you had just said, I don't care that the BO number to check the validity of lump capacitance is so high. I just want to use the lump capacitance anyway. It'll give you a number. It'll give you a number. If you assume or use the lumped capacitance, which I just to check it, you get a time of 86.6 seconds or 87 seconds. Less. If you assume lumped capacitance is true, there's no resistance to the heat transfer inside. The temperature at the center is the temperature at the edge. It'll cool faster. Is that right? So there you go. Well, with that, I have covered a lot of material. Sorry I didn't plow deeper, but you have a whole course in PDEs. Right? It's time to review if you want to. And next time we'll move into semi-infinite solids. Thank you very much.